So we'll do practice exam from Unit 1, key. So a couple problems here. There will be multiple choice questions as well. And some of these like short answer. So these first couple, need to know E and Z, the designation for E and Z. You gotta show your work for this too. So E, Z, or neither. And of course, E and Z are for alkenes, right? So you split the alkene down the middle. And then you rank the two things off each side of the alkene. So carbon to carbon is a tie. This carbon's bonded to 3 hydrogens. Carbon, 2 hydrogens, so this one wins. Same on this side, so they're on opposite sides. That's an E. Over here, again, split it down the middle. The key is 1 bond out at a time. So fluorine versus carbon, fluorine wins. Right? It doesn't matter that bromine has a higher atomic weight. You go 1 atomic weight, 1 bond out at a time. Fluorine wins both sides, so this is Z. For this one, you need to be able to do ring flips still. That's the first part, is just really make sure you know how to do ring flips. And then the other part was to make sure I wanted you to circle the worst leaving group. So this would be something to be the least stable. Right? Something to be the least stable with a negative with electrons. So this is imagining electrons go here, electrons go here. Right? That's what this is imagining. So you could have OH minus, NH2 minus, Cl minus, or water. So water would be the most stable. Then it'd be Cl minus because it's more electronegative and big. And then O minus versus N minus. N minus is the least stable because it's less electronegative. Right? So it's going to be more reactive with the negative charge. So that's why that would be the worst leaving group. So number 3, we're going to try to determine the following. What these pairs of things are to each other. Are they constitutional isomers, enantiomers, diastereomers, or are they identical? So this is kind of like, you got to know just kind of definitions of these things too and look at them. So enantiomers and diastereomers all have chiral centers, right? And diastereomers have to have at least 2. So this one, right, of course, chiral centers are asymmetric centers. sp3 hybridized, bond to 4 different things. I see 1, 2. 1, 2. So 2 types of chiral centers. So this could be enantiomers or diastereomers. Or they could be identical. They're not constitutional isomers. They have the same bonding pattern. But if you look at this, wedged and wedged, dash and dash, and they're on the same side, these are actually enantiomers. Everything's flipped. So these are enantiomers to each other. For this one, the cyclobutane and this alkene, they have the same number of carbons and hydrogens, but they're obviously bonded differently. So these are constitutional isomers. And then these two are actually identical. So one of the things that's tough here is that people look for the wedge. So methyl's wedged, H dashed, H wedged, methyl dashed. Like, oh, it flipped around. But I also moved the OH from left to right as well. So these are actually identical. So if you went through and did RNS for this, you'd know that. But you could eliminate, this can't be a diastereomer because there's only one asymmetric center. They're not constitutional isomers because they have the same bonding. So then you're kind of stuck between identical and enantiomers. But you could figure it out. That's a tough question. Okay, on that one?
That last one.
Go ahead.
Yeah, and that last number 6.
Yeah, the one on the far right, because I looked at the center, it's like, is bonded to 2 oxygen.
The reason why this is not the same is, yes, this oxygen and this oxygen. But if you keep going out, is it exactly the same, like split down the middle? Like if you, like all of a sudden, this, if you keep going out, there's something else on this side, right? If you divided this in half from here, it's not exactly the same on either side. It is in the short term, but as you keep going out, it gets different. All right, for this one, looks like I gave you the reactions and asked for the mechanisms, but I could ask you for the types of reactions. So the first step is proton transfer. Again, what I told folks to look for, if you see H plus or OH minus, things with charges, they're going to react. They should react first. Proton transfers often involve lone pairs, right? Either from an OH minus or lone pairs from an OH and NH and SH or pH, grabbing an H plus. All right, so that's the proton transfer. That makes water a good leaving group. Second step is leaving group leaves, so it just falls off one step at a time. Makes the carbocation. Then there's resonance, different arrow. Move the pi electrons over. Carbocation is now here. Solvent adds. Now the solvent adds in. So this is also an SN1 reaction, right? You could diagnose this reaction, right? You could see that It's a tertiary or secondary allylic, so that could be SN1 or SN2. It doesn't have a reactive nucleophile, and the solvent is polar protic, so that tells you SN1. Solvent adds in. Biggest things, nothing happens to the hydrogen or these two carbons, they're still there. So don't do anything to those, just the lone pairs and the oxygen are taking the oxygen there to form a bond. Final step is regenerating the catalyst, is the catalyst. So H falls off, make sure the electrons go the right direction, right? Which direction do the electrons go? They go towards the oxygen, right? The hydrogen never takes electrons, right? Oxygen gets those electrons back, and that gets us to our final product. All right, looking at a rearrangement reaction. So these were ones, so clues, I told you it's rearrangement reactions. It looks like carbons are moving, right? So these are all carbon shifts or methyl or carbon shifts. And so the reason why they're doing this is because you have a secondary carbocation, and now you see there's a new methyl here. So it doesn't matter which one you pick, but the 2 electrons and this carbon go right there to that atom. So this carbon got a new bond, this carbon lost a bond, so it has a plus charge. As you can see, what bonds are broken and formed here, this ethyl, this whole piece, these 2 electrons move with the 2 carbons attached to it over to there, to make a tertiary benzylic carbocation. So the reason why it happens, secondary, tertiary is more stable than secondary, and then tertiary benzylic is more stable than tertiary, because now this can do resonance. Then our old friend resonance comes to visit once again. People got kind of thrown off on this, they kind of forgot, and then they re-remembered. Right, all resonances is moving p orbital electrons in p orbitals. So in this case, you're just moving the pi bond, pi electrons, form a new pi bond there, plus charge here, pi electrons, plus charge here. So that's all this is. Still got to know how to do resonance. All right, so this question, on the mechanism of the product. So I'm telling you it's an SN2 reaction, so that should clue you into something, right? If I just gave you this without other information, it'd make it a lot harder, but I told you it's an SN2, right? You're responsible for knowing how to do SN1 and SN2 and those rearrangements, really, for this. This is a big part we talked about. So SN2 the substitution part happens in one step, 2 arrows. Nucleophile, electrons start at the nucleophile, need to come from 180 degrees away to the carbon, that's the electrophile. And it kicks that out. Remember, that's that backside, so it does inversion. Right, so you gotta remember it does inversion. One thing I want to make sure you don't do is, so this carbon right here at the wedge is just along for the ride. Nothing happens to it. Right? The arrows no electrons ever go to it or away from it. It's just there. So it stays the same the whole time. Because it's coming from the backside, so if this is dashed, 180 degrees away would be wedged. And so this nucleophile, the nitrogen ends up being wedged because it had to come from 180 degrees away, because that's where sigma star was. So that's what this had to be wedged as well. Let me just do this now. So just imagine, so this is SN2, but if this was SN1, you would have 2 products. What would you have? You'd have this wedged always, that never changes, and you'd have this wedged, but then you'd also have the other version, which would be what? So one thing I'm seeing people miss
Are you talking about
this.
the racemic mixture?
Yep. So
that?
Yep. So if it had been SN1 and maybe this had been NH2 polar protic, you'd make something like this. But people were kind of missing the ability to draw both products, right? I think one of the examples was, right, there'd be OH over here, and then I don't know what these were, but then have the OH over here, right? So this is another way of viewing, right, 2 different things. The OH is on the left, OH is on the right. Nitrogen's wedged, nitrogen's dashed, right? So those are showing 2 sets of differences. For SN1, you get 2 products. All right, another rearrangement reaction. How do I know it's a rearrangement? I'm telling, right, read your instructions carefully. Make sure you do that. I'm telling you it's a rearrangement reaction. Also, the equilibrium reaction arrows. So what happens here, we go from a secondary with a cyclobutane, right? Cyclobutane. And I numbered these carbons for you to hopefully make this easier. And so the bond that needs to break, right? So when you're doing rearrangements, you're looking for single bonds 1, 2 bonds away, right? So secondary, this has 6 single bonds 2 bonds away, hyperconjugation buddies. So what needs to happen is if you look here, what bonds broken, what bonds were formed. If you look here, like 3 was bonded to 6, but it's no longer bonded to 6. And now 6 is bonded to 2. So the electrons between 3 and 6 need to go there, moving 6 to be bonded to 2. That makes a 5-membered ring. And that's secondary. And then the hydrogen, right, will shift again, do H shift, to make a tertiary, which is more stable than secondary, more hyperconjugation buddies. And so that's why that last step happens. Circle the mesomolecule. Let me give you the hint. You are a mesomolecule. Why are you a mesomolecule? Because you have asymmetric centers like your hands. They're either RS or your feet are RS, but you have a mirror plane. This one doesn't work because you can't cut it in half. It has asymmetric centers, but you cut it in half, you don't have a mirror plane. You cut this one in half, you do. Both F's will be looking at each other. The reason why these two don't work is because this is a CH3 and this is an F, so there's no mirror plane there, right? This doesn't work, and same with this one. So looking for that mirror plane with asymmetric centers. So for this one, explain what evidence tells you about the type of mechanism, either SN1 or SN2. So a rate triples with 3 times the electrophile, but no change in the rate with 2 times the nucleophile. So that's just really like, do you know the rate laws for SN1 and SN2, right? In an SN2 reaction, both the nucleophile and the electrophile matter for the reaction, for the rate. And in SN1, it's all about the electrophile, right? It's all about that leaving group leaving. So if the rate changes the electrophile, that could be SN1 or SN2. But if nothing happens with the nucleophile, it has to be SN1. Because SN1 rate law doesn't depend on the nucleophile. This one, a primary alkyl halide, so this is a primary electrophile, reacts faster than a secondary alkyl halide. Well, that just matters of what kind of electrophiles work. So primary means not very sterically bulky, right? And you can't make a primary carbocation. We talked about that. It's not stable. So it has to be SN1. So primary, less sterics, and can't make carbocation. So that tells us it's probably an SN2 reaction. This one, the rate increases with an iodine leaving group versus a chlorine. So iodine's a very good leaving group because it's large. All right, it's polarizable. But that works for both SN1 and SN2. So because basically the electrophile is in both rate laws, right? Both want good leaving group as in each rate law. So right, SN1 and SN2 both involve electrophile, which has the leaving group. So a good leaving group is good for both.
And is that because...
All right, so 11, type of reaction in the box, right? Proton transfer, leaving group leads, add, substitution, elimination, rearrangement. So those are, I give you all the possibilities. Give the mechanism arrows. So here, again, you see OH minus, right? You see OH minus. If you look at what happened here, I should have drawn in water. There should be a water here. But you could probably figure out where it went. That H, obviously, if this H came off, that's a proton transfer, right? You end up with an O minus. So electron, arrow started electrons, go to the H, break the OH bond, right? Proton transfer, that's reaction. Here you can see the Br minus, this is a substitution reaction. It's like an SN2 reaction really, because it happens all in one step. There's no carbocation. So backside, primary electrophile, alkyl halide, get the substitution reaction. So if we remember, we talked about the 5 factors that affect reactivity. We talked about electronegativity, right? Who holds it? How much an atom wants to hold on to its electrons, whether it wants to let them react or hold on to them tighter. Size, larger atoms are more likely to give up their electrons because they're farther away from the nucleus, right? They can be more stable too. It's just different. It depends on lots of factors. We talk about resonance, when resonance can do things. We talked about induction, which is just like electronegativity from far away. And then we talked about hybridization state, and that's what this is about. So you have SP versus SP3. And so if you go back through and you look, SP hybrid orbitals are closer to the positively charged nucleus. So that makes them less reactive because they're held tighter. It's almost like electronegativity, but it's not really. And the SP3 hybridized electrons are farther from the nucleus, so they're more reactive, they're more willing to react, there's more space. And so their lone pairs in sp3 orbital are more reactive as further from the positively charged nucleus. So that's the deal there. All right, last one, drawing mechanism, arrows and products of each reaction. Again, all your steps are given here, so make sure you slow down and follow those things along. This one's pretty tricky, this first step, because both things are neutral, right? There's no plus charge or minus charge. But if you look at what needs to happen, right? Well, I need to get an H on this oxygen here somehow. And if you remember that this, of course, is a carboxylic acid functional group, that'll help you realize this. So the first step is a proton transfer. So it takes that H, breaks that OH bond, makes this piece here, the carboxylate, actually with a minus charge. Leaving group leaves. So leaving group leaves. We make a carbocation. We have an H shift, a rearrangement. So we go from secondary to, now the H shifts over. Notice the electrons move, what takes the atom with it, to a secondary allylic, which is more stable. We do resonance, different arrow. We get tertiary allylic. And the last step is just the addition of what's the minus charge is left over, adds in. That's the addition of the solvent and gets us to the final product. Biggest things, balance your charges, slow down one step at a time. All those kind of good things. Plenty of time to take the test. Make sure you slow down. So a really good question, right? Do we have to do the proton transfer first? Well, first, I told you to, so you just got to do it that way. But why that is because this versus this, which one's a better leaving group? So an oxygen with a plus charge is much more unhappy, wants to take these electrons, than something that doesn't. So you need to protonate it to make it a better leaving group. So that's why that happens first. That's why the proton transfer happens first.